Hello. Briefly today, I want to review the definition of the Riemann integral, at least our definition of the Riemann integral. There are certainly different ways to set it up. And then um, I'll also look at a graphical interpretation of the Riemann integral as signed area under the curve and see how both of those interpretations can inform some nice properties of the Riemann integral. So here is our definition, just to recall quickly. You have some function on the real numbers that we'll call f. It's continuous on some interval ab. And our Riemann integral we define to be the limit as the number of rectangles goes to infinity of the sum of all the height times width, which gives us area, right, for all of the rectangles, right? The sum of all the rectangle areas as the number of rectangles goes to infinity. Then how do we get these heights and these widths? Well, the widths are calculated by saying how wide is the interval and then divide it into n equal pieces. That gives you the width. How are the heights calculated? Well, we pick n points equally spaced across the interval, which we do by starting at a and then adding n times delta x as n goes from 1 to big N. And that's how we get our x values. And then we evaluate f at those x values, because f at those x values gives us the height of each of those rectangles. So this is our definition of a Riemann integral. And here's a picture showing it represents the area under the curve, signed area, more precisely the signed area under the curve, because you're taking a rectangle plus 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 a rectangle, and right. So you're taking all these little rectangles, adding up their areas, and then as the number of rectangles goes to infinity, the area becomes perfect. Note here in this picture, a typically is a real number. Less than or equal to b is how we imagine this, right? Usually that's sort of implicit to our notation. Our interval notation is usually implies that a is less than or equal to b. So now let's look at some properties. Here is a nice property of the Riemann integral. Suppose you integrate from a to a. You integrate a function from a to a. I claim that gives you 0 as the area. Why? Well, we're integrating from a to that same point. We don't move left or right at all. So this region has no width. It only has height. Therefore, it has area 0, right? So by looking at the graph, thinking of that geometric definition as assigned area under the curve, it makes sense that this integral should be 0, no matter what the function f is, right? Now, can we confirm that with our definition, our limit sigma fx sub n times delta x? Can we confirm it with that definition? Yes, absolutely. B equals a in this setting, right? Because it's from a, instead of a to b, it's from a to a. So b is equal to a. Plug that into the definition for delta x. Instead of b minus a, now we have a minus a in the numerator. So the numerator becomes 0, which means that fraction equals 0. This is, notice, this is different than just saying that delta x is a quantity that approaches 0 as big N approaches infinity, right? That's always the case. We always have that delta x approaches 0 as big N goes to infinity. Yes, the width strength to 0. That's not what we're saying here. I'm very purposefully not writing limit as in this expression. We're saying that delta x equals the constant 0, no matter what big N is. Very different scenario. So if you take that delta x and plug it into our definition of an integral here, you get that the integral equals the limit of the sum of the function times 0. Delta x is just 0. Therefore, we have a limit of a sum of a bunch of zeros, which is 0. The limit of 0 is 0. Right? So there's sort of a graphical interpretation of this property, but also an interpretation of this property coming directly from that Riemann sum definition. Now, let's look at another one. Here's another property of integrals. The integral from b to a of f of x equals negative the integral from a to b of f of x. So if you think of it graphically, what this is really saying is, we're again, think of b as the bigger number, right? So this is sort of saying you're integrating to the left. You're integrating from b to a instead of a to b. Well, you could think of that as negative widths on your rectangles. Just like we allow negative heights on our rectangles if f happens to be below the x-axis, here we're seeing negative widths on our rectangles. So it makes sense that this, graphically, that this would be negative of the value you would get if you went from left to right. and had positive widths. You can also confirm this with the definition, just like we did previously. What's our formula for delta x? Well, if you're going from b to a, your numerator on delta x is going to look like a minus b, because a and b were interchanged, right? So instead of b minus a over n, you're going to have a minus b over n. Then this expression in the numerator, you could factor out a negative to get negative b minus a, right? It's the negative of the normal delta x, right? What delta x usually looks like, b minus a over n. Why are they the same? Well, look at that negative sign. If you distribute it to the b, you get a negative b. If you distribute it to the a, you get a positive a, which is what we have on the other side of the equal sign. So they're equal to each other. So this is why these integrals are negatives of each other, because they really have the same delta x, except they're just off by a minus sign, right? When you interchange a and b. Now there is one subtlety to think about: the x sub n's. Something slightly different happens with the x sub n's for this integral versus the x sub n's for this integral. Is these x here x sub 1 starts actually at b, and then go back by delta x, and here I mean the regular delta x, right? That would be your first point, and you would never use b, right? And then the very last one, the x sub n, would be a. As opposed to over here, you would have x sub 1 would be a plus delta x, again meaning the regular delta x, and then you would go until x sub n would become b. By the way, we defined our points, right? Our x sub 1 through x sub n. So you do get slightly different x values that you're evaluating at. However, as the limit goes to infinity, as the number of rectangles goes to infinity, then whether you have this one point chosen way at the extreme left or this one point chosen at the extreme right of your Riemann sum makes no difference in the quantity, since that particular rectangle will go to 0 on either side. So all right, so there's a bit of a technicality to address there with the x sub n's, but most, really what's representing the behavior here is this a minus b equals negative b minus a, right? That's really what's driving this identity. So, all right, great. So we have two common identities that you'll see in the context of integration, right? Integrals, especially with bounds, and they follow not only from the graphical definition of an integral, but the way of thinking of it as signed area under the curve, but also from the formal definition as a Riemann sum. Great, thank you.